Welcome to this session on scaling NVMe fabric security. I'm Claudio De Santi from Dell. So this is our agenda. We will first take a look at the currently defined security functions, and then we will dive into them, looking specifically on DH-HMAC-CHAP authentication, how that is helped by an Authentication Verification Entity. People are still coming. Please sit down. And then we will see how this Authentication and Verification Entity, or AVE, can be accessed, and how that simplifies the provisioning for DH-HMAC-CHAP. So first step, security functions. Storage security requires two fundamental functions. One is authentication, so a proof of identity. Every time you connect to an NVMe entity, the entity is identified by an NQN. That is the identity of that entity. And so authentication is a way to prove that, yes, you are really who you are claiming to be. Second point is secure channel, a way to guarantee integrity and confidentiality of data in flight. So each packet or each TLS segment in this case would be encrypted and have a integrity checksum that enables to verify by the receiver if data has been altered or if has been, and guarantees that no one can see it. So this is both integrity and confidentiality. NVMe defined the two protocols for these functions. In TP 8006, which is now fully integrated in the base specification 2.0, we defined for authentication DH-HMAC-CHAP. And for secure channel, we defined how to use TLS 1.3. This has been done in TP 8011, which is now included in the NVMe TCP transport specification 1.0. And the question that we have here is, how do we deploy at scale in a fabric these two functions? This is an example of an authentication of a host and a controller. And the way in which we define this thing is called bidirectional authentication. You have a session establishment within host and controller. You have your connect command that set up queues and associate the host to the controller, as you can see here. At this point, an authentication transaction can happen, and this enables the host to authenticate the controller, so verify the identity of the controller, and the controller to authenticate the host, so verify the identity of the host. At this point, the queue is ready for subsequent operations, and the two parties has been both authenticated to each other. So this is the way in which we define an authentication of two entities in NVMe. Another thing is we defined the usage of TLS 1.3. TLS 1.3 defines a secure channel using the same protocol that is used right now. Every time you connect to your bank account on your web browser, you are using TLS to connect there. Okay, that's what is used here. So you establish a secure channel, and now everything is integrity protected and encrypted for confidentiality over this secure channel. You do your connect, that set up queues and associate those to the controller, and we are ready to go. What is the problem of TLS 1.3 that we have? The way in which we define a TLS, as has been done in most other storage protocols, is based on pre-share keys. In order to authenticate and establish a secure channel between two NVMe entities, these two entities need to know one specific pre-share key, one specific PSK. And each pair of entities require its own PSK. This is a quadratic problem. If I have n host, m controllers, m subsystems, I will need n per m PSKs to manage and configure everywhere on my fabric. In order to try to address this problem, these scalability issues on the provisioning side, authentication protocols, we added one step to the authentication protocol to help. We basically invented this concept of a secure channel concatenation to an authentication transaction, which is all defined in NVMe 2.0. Upon successful completion of an authentication exchange, while two entities are authenticating each other, the two involved entities are able to generate a shared session key, basically a PSK, which is computed on the fly. At this point, you can use these PSK to perform your TLS negotiation. In this way, what you get, the TCP connection begins as secured and then transition to secure. This is called opportunistic TLS in literature. It's used as an example by SMTP. It's not something new. It's quite well used in the internet. And now, what we get in this way, we are reducing the TLS provisioning problem to the DH-HMAC-CHAP provisioning problem. If that can help, okay, we are able to resolve the problem over there. And this is the way in which now an establishment of a TLS session concatenated to an authentication transaction is performed. You start on TCP, you perform your connect, you authenticate the two parties, you generate a PSK on the fly. Now that PSK enables to establish the TLS secure channel, and at this point you are with your queues set up and everything is running over a secure channel for every IO. So what we did in this way, what has been done, as I said, we transformed the provisioning problem for TLS into the provisioning problem for DH-HMAC-CHAP. Let's take then a deeper look on how DH-HMAC-CHAP works and how the security parameters for DH-HMAC-CHAP are provisioned. So the way in which DH-HMAC-CHAP authentication works, an entity, could be a host or a subsystem, is provisioned with a key, its own key. And the purpose of the protocol, DH-HMAC-CHAP, is demonstrate that you know your key. So a controller will authenticate a host if the host demonstrates that it knows its own key, KH. And a host authenticates a controller if the controller demonstrates that it knows its own key, KC. How do you demonstrate this key knowledge? Is a challenge response protocol. The key is not passed in protocol messages. The key stays on the entities and is secretly kept over there. The authenticator, so the entity that is trying to authenticate the other entity, send a challenge. The responser computes a response using its own key. And the response is done by using this HMAC function, using the key of the responder as key, and using the challenge as the parameter to compute the response, plus additional things. And we will see that. The authenticator receives this response, the authenticator verifies the response. So how does the authenticator to verify this response? Needs to know the key of the responder. And so the authenticator computes the expected response R prime. This is what I expect. When I send you this challenge, I'm expecting you to give me this response. And so if you get that response, means, oh, you are really who you are claiming to be. It means you are knowing your key. If you get a different response, authentication is failed. That's the way in which the protocol works. Let's look it at a diagram. Will be easier. So suppose you have a host and a controller. First step, you have the key provisioning. Host will have my key, KH. The controller has my key, is KC, the key of the controller. And I will need a verification key to authenticate the controller and a verification key to authenticate the host. The protocol begins with an auth negotiate message. Carries a transaction ID, a flag for the secure channel concatenation, what we said before, to concatenate TLS here. The identifier of the security protocol, the identifier for the DH-HMAC-CHAP, a list of hashes that can be used for this authentication transaction, a list of Diffie-Hellman group IDs that can be used for this authentication transaction. The controller will pick one hash and a Diffie-Hellman group to perform the authentication and send its response, the response message, which is the DH-HMAC-CHAP challenge message. That carries the transaction ID, okay, we are continuing this transaction, the specific hash that has been selected by the controller, and that will be used for the authentication transaction, the specific Diffie-Hellman group that will be used for this authentication transaction, a sequence number, the challenge. That is the challenge that the controller is sending to the host to authenticate the host. So in this transaction, the first step is for the controller, for the subsystem, to authenticate the host that is trying to access the subsystem. And then I have the Diffie-Hellman parameter, G2DX mod P, associated to the specified G. What the host does, computes a session key, which is based on the Diffie-Hellman exchange that is happening over there. From this key computes an augmented challenge. That is how the Diffie-Hellman exchange is used to improve the security of the CHAP protocol. And then compute the response. As I say, the response is an HMAC using the key of the host, my key, to this set of parameters. The augmented challenge concatenated with the sequence number, concatenated with the transaction ID, concatenated with the secure channel concatenation, concatenated with the string host, I'm on the host, and the Q and QNs of this transaction, the QN of the host and the QN of the controller. That is the response that the host computes to the challenge that has been received. And that response is passed to the controller. So this is the computation of a response to a challenge. Now, the controller has to verify this response. That is the next step. So this is why I put these two colors for computation and for verification. And so what does the controller has to do? Same process. It computes the session key based on the Diffie-Hellman exchange, computes the augmented challenge, which is based on the session key, and then computes the expected response, R1 prime. And in order to compute this expected response, it uses the verification key that has been put here, because now we are on the verification function. So use KH. Performs exactly the same computation as the host does, and so if the final result R1 prime is the same as R1, okay, the authentication is successful. It means the host knows the key H that the controller knows. If instead the received R1 is not the same as the computed, the expected R1, then the authentication is failed. That's the way in which a controller authenticates the host on this challenge response protocol. Of course, the host in the DH-HMAC-CHAP reply message can send also a challenge to the controller so that the host can authenticate the controller, verify if the controller is really who is claiming to be. And so the controller has to respond to the challenge CTU. And the way it does the response is exactly the same math. Compute the session key, compute the augmented challenge CATU based on the challenge received and the session key based on the Diffie-Hellman exchange, and then compute a response R2, which is computed exactly in the same way. But look, the difference, now I'm using KC, I'm using my key to compute my response to the challenge that I received. So the controller is using his own key to compute the response R2 to the challenge CTU that the controller received. And of course, use that key to compute an HMAC of this parameter. And the augmented challenge, the sequence number STU that has been sent by the host, the transaction ID, the secure channel concatenation flag, the string controller, and the Q and QNs again that are used, that are now participating to this authentication transaction. This R2 is now sent to the host in a success1 message, assuming the previous authentication, of course, was successful. So now the host received the response R2 to this its challenge CTU to the controller, and it has to do the verification step, which is exactly the same that the controller that had done before to verify the response R1 of the host. compute the session key, compute the augmented challenge CA2 based on the session key, and compute the expected response R2 prime based on the verification key, which is KC. I'm verifying the response of the controller. And if the expected response is the same as the response I received, authentication is successful. Otherwise, authentication is failed. So this is how DH-HMAC-CHAP works. And this is what we define in TPA 8006. Let's look at the provisioning problem of this thing. Suppose I have my fabric with N hosts and M subsystems. And I want, as an example, subsystem S1 to authenticate all the hosts. Now what I need on the subsystem, I need my own key, my computation key, to compute my responses to the challenges that the hosts are sending me. But in order to verify the responses of each of the hosts, I need the list of each host verification keys. So I need to maintain for host H1, I need the key of H1 so that I can authenticate H1. For host H2, I need the key of H2 so that I can authenticate H2. And this is the same for all subsystems. It means I need to put all these, the verification keys of all hosts on each subsystem. Conversely, if I'm looking at the host side, the protocol is symmetric, so you can immediately see what we are expecting to happen here. Suppose host H1 want to authenticate the M subsystems. Again, I will need my own computation key to compute my own responses to the challenges that a subsystem are sending to me, KH1. But for each subsystem, I will need the subsystem verification key. For NQN S1, this is the key to verify the subsystem S1. For NQN S2, this is the key, KS2, to verify the subsystem S2. So I need to keep on each host the list of the verification keys for each of the subsystems the host can communicate to. Let's look at an example. Let's consider a fabric not even too big, 100 hosts, 25 subsystems. And suppose that whole host want to authenticate all subsystems. So each host needs to be provisioned with his own key and the 25 subsystem verification keys. And what happens when I add one subsystem to the fabric? All 100 hosts needs to be reprovisioned to add the additional subsystem verification key. Otherwise, I cannot authenticate that subsystem. Same on the other side. Initial subsystem provisioning, each subsystem needs to be provisioned with its own key and the 100 host verification keys. And when I add a host to the fabric, all the 25 subsystems need to be reprovisioned to add the additional host verification key. Stated in other words, plain DH-HMAC-CHAP authentication is fairly difficult to deploy. The provisioning problem here is not trivial. Every time you add or remove something to the fabric, you need to update your security provisioning on every entity of the fabric. This is why we invented the Authentication Verification Entity, to drastically simplify this problem. What is this Authentication Verification Entity? It's an offload of the verification processing through a single complete database of NQN, key records. So imagine your fabric, N host and M subsystems. Now I have an AVE in my fabric, which keeps this database of NQN, key records. NQN of the host, key of the host, NQN of the subsystem, key of the subsystems. Now, if I have these things and all the entities are able to connect with the AVE, how does the authentication protocol change? Not very much. Same thing. You provision the host and the AVE with the key that you have, host or subsystem. The authentication is exactly the same. You need to demonstrate that you know your key. So controller authenticates the host if the host demonstrates it knows its own key, and the host authenticates the controller if the controller demonstrates that it knows its own key, KC. The demonstration is the same. Send a challenge, compute a response based on the key of the responder, And now the authenticator has to verify the response. This is the difference on the response verification. Now the response verification is delegated to the Authentication Verification Entity. It is not performed locally by the authenticator, which is consistent, by the way, with the reduced model for iSCSI-CHAP. So how does the protocol changes? Now, what I need to do in terms of key provisioning, the host will be provisioned with the key of the host and a way to access the AV. The controller is provisioned with the key of the controller and a way to access the AV again. Here we have the AV that will have the key of the host. I'm looking on authenticating the host. And of course, we'll have also the key of the controller. So this first step of the authentication protocol is exactly the same. Start with an or negotiate, you get a challenge, the controller is challenging the host uses his own key to compute the response R1 is sent back to the controller. At this point, what the controller should have done before was to compute the expected response and verify if the expected response is the same as the received response. Instead, rather than doing that, the controller requests the AV to verify on its behalf. Hey, I'm doing an authentication transaction with this host, NQNH. These are the parameters of the authentication transaction, the transaction ID, the secure channel concatenation flag, the hash ID that I'm using, the sequence number I received, the augmented challenge I need that I sent. This is my NQN and R1. This is the response I got. Is this the proper response or not? That is the query to the AV. The AV processing, what does it do? Look up the key of the host from the NQN of the host that is requested to the AV, computes the expected response, and verify if the expected response is the same as the received response. And if it is the same, the authentication is successful. And so what is returned by the AV to the controller is, yes, authentication is successful. Done. At this point, okay, the controller will have received its challenge C2. And so the controller has to reply to the challenge. So it will have to use its own key KC to compute the response R2 to the challenge C2. Same processing. Compute the session key, augmented challenge, compute the response based on the key of the controller. And that is sent back. And now the host, what does it do? As I said, it does not perform this computation by itself. Instead, it requests the AV to verify, hey, I'm trying to authenticate controller having NQN and QNC. This is the transaction ID of this transaction. This is the secure channel concatenation. This is the hash we are using. This is the sequence number S2 I sent to him. This is the augmented challenge. This is my NQN, and this is the response R2 that I received. Is this the right response or not? The AV does the lookup of the key of the controller, computes the expected response, verify if it is the same. If it is the same, authentication is successful, otherwise not. So this is just a delegation of the verification function to this authentication verification entity. That's why it's called authentication verification entity. We are delegate the verification function over there. What happens in terms of provisioning once we introduce the AV into the picture? Suppose look at subsystem S1, which is connected to the AV. Okay, in order to authenticate all these hosts, now everything I need is my computation key, the key of the subsystem, and a way to access the AV. I don't need anything else. And this is completely independent on what any other entity of the fabric does. If the host uses the AV or not is completely independent. It's fine. And so, and this is the same thing for all the subsystems that are using the AV service. I drastically simplified now my provisioning information. I just need to put 2 things rather than many for the fabric. And if I look at the host, it's actually the same thing. Look at the host that is able to access the AV, which security provisioning information do I need to put over there? The computation key of the host, okay, H1, and a way to access the AV. That's it. And in this way, the host is able to authenticate all the subsystems. And again, the host provisioning is totally independent on subsystem provisioning of what other hosts are doing. That host has a way to verify all the responses and so to complete the authentication without the need of anything else there. Same for the other hosts. So let's look at an example, same example before. How does the protocol scale once we have an NVe in the picture? Consider the same fabric with 100 hosts and 25 subsystems, and suppose that all hosts want to authenticate all subsystems. Now, each host needs to be provisioned with its own key and a way to access the NVe. And if I add a subsystem to the fabric, I don't need to touch any host. I just need to be sure that the additional subsystem key has been added to my centralized verification server, the NVe. So I don't need to reprovision anything in the fabric. Same on the other side. Initial subsystem provisioning, I just need to put this own key and a way to access the NVe. And when I add a host to the fabric, there is no need to reprovision any subsystem. And so this is the comparison. I put the two examples together. So an authentication verification entity makes the DH-HMAC-CHAP provisioning scalable. That is what we achieve with this additional entity in the fabric. And we get basically something very close to an ideal fabric authentication provisioning. You want to have a minimal initial provisioning, no need for endpoint provisioning during fabric changes. You have a consistent behavior, so what you do on one system is independent on what the other entities are doing. Things automated, you don't need to do anything manually, but you want protocols that take care of all the steps for you. So the resulting deployment model is provision authentication once and forget about it. One possible thing in this regard, when you do your initial system provisioning, you could put your key, let's say your BMC, and then during booting of any other moment, you can retrieve that key from there, and from there everything happens. So you do your provisioning once, and then security is fully automated over the fabric. So let's now see how. There is one step we still did not look at. I say we need to access the NVe. How do we access the NVe to do that? We need to have a communication authenticated and protected, because of course now the authentication verification entity is a database of all the keys of your fabric. It has to be very well protected. So only authenticated authorized entities are allowed to access the NVe. So only the entities that are listed in the NVe database. And you need to have integrity and confidentiality to protect the information exchanged. Otherwise, even though you exchange the augmented challenge, you lose the augmented security of the Diffie-Hellman exchange that happened during the DH-HMAC-CHAP protocol. Common way in which, as an example in Linux, TLS and DH-HMAC-CHAP has been implemented is represented in this diagram. We have in the kernel driver, we have the kernel TLS function and the DH-HMAC-CHAP function has been implemented with the possibility of TLS concatenation represented by these arrows here. So if I have this situation in which I have a kernel TLS function available and a DH-HMAC-CHAP function in the kernel, this means that this host or this subsystem this host, I'm looking at a host at this moment, is able to access a subsystem over a TLS channel. I implemented it. So if I use the same protocol to access the NVe, I don't need to have any user space interaction as an additional way to interact with the NVe. I can use exactly the same protocol. I enable a kernel implementation for the NVe access. And that is what we decided to do. So use the same TLS protocol that we defined in TP 8011 also to access the NVe. And so after all these things, how does all this provisioning of the DH-HMAC-CHAP and NVe get down to? For an NVMe entity having a certain NQN E as NQN, need to generate a random key KE. a random TLS PSK to connect with the AV, PSK, and then you add to the AV database the record, this entity has this key and this PSK to connect with the AV, and provision the key, the PSK, the QN and the AV to the NVMe OF entity. That is the single step you have to do. After that, everything else is automated. So let's look at another example on how DH-HMAC-CHAP would work with an AV. Initial provisioning. As I say, you put on your AVE per each entity, the key of the entity and the PSK to communicate with the AVE or that entity. On the controller, its own key, the PSK for the AVE and the NQN of the AVE. In the host, the key of the host, the PSK of the host, and the NQN of the AVE as well. These enable this channel, TLS channel, to be established with AVE. Now you can have your TCP session establishment with your NVMe OF connect command. You perform all your DH-HMAC-CHAP and you leverage the AVE for the authentication verification function. So everything I need to have, I need N plus M keys, N plus M PKs in order to support N per M authentication. So I need a linear number of keys, not quadratic. I drastically reduce the problem there. And it's just a one-time configuration. So I provision one DH-HMAC-CHAP secret, and this enables an arbitrary number of authentications over my fabric. This becomes even more powerful when I concatenate TLS to these things. Because what it means, during this DH-HMAC-CHAP transaction, a session key is now generated between this host and controller. This session key enables to transform the admin queue from simple TCP to TLS and establish all IO queues directly in TLS. And so, in this way, what I got, with one secret, one DH-HMAC-CHAP secret, I'm able to support an arbitrary number of TLS channels on my fabric. Summary, we are there. Provisioning of the currently defined NVMe security protocols is something that does not care, we said before. TLS requires provisioning one PSK per each pair of entities of an NVMe fabric, and plain DH-HMAC-CHAP requires provisioning verification keys. Adding the DH-HMAC-CHAP verification, authentication verification entity to the NVMe architecture makes the provisioning of this protocol completely scalable, because it enables to provision authentication once and forget about it. This is something that has been worked out in TP 8019, which is currently in integration phase, ready for ratification almost. And that's it. Questions? Please, begin there.
How's the initial enrollment done securely?
Sorry?
How's the initial enrollment, initial provisioning done securely?
The problem there is not something that is defined by the spec. First of all, repeat the question. How is the initial enrollment done securely? Basically, each system has its own way to do it, and that is reality today. If you deploy host from one vendor, each vendor has his own way to do initial provisioning of systems, but there is no standard way to do it over there. So you basically leverage what you have over there. Worst possible case, you take your USB key, you put over there one key, and you go around on your host to do the thing. I consider that the worst possible case, but still, it's a possible way in which you can do your initial thing. As again, as the example I said before, if you are doing your initial provisioning of a system, you can store the key of the system into the BMC as part of the initial provisioning, whatever you are doing that usually happens on a secure channel. That's enough. At that point, everything else can take the key securely from there, and you don't need to do anything else. Roger.
What's the security requirements of these initial keys that you're programming into the AVE? Basically, the AVE's got all the keys for the work, right? The initial shared secrets?
The initial requirement is a PSK, and so you so repeat the question. What are the requirements for the key that you need to configure in order to access the AVE? all these keys are just long enough random numbers. Be sure you have a pretty good random generator. And so the minimum one is based on SHA-256, or 256 or random numbers, 256 bits, random bits. Better choice would be 384 based on the SHA-384 hash. So, but you support also SHA-512, and so 512 random bits. So what are these keys? String of random bits. The three lengths supported are 256, 384, 512.
Are they publicly known?
No, they should be known.
While you're provisioning the
You need to have a secure administrative channel to the AV. Your console to the AV has to be a secure channel.
somebody's looking at a key and putting it into the AVE, right? And the storage in the AVE.
That is an implementation detail of how you implement these things. Whenever you have authentication servers are available in many places or so on, whenever you have to store some secret information, okay, there are ways in which, okay, you encrypt what you are storing to be sure that everything is protected and so on. And you follow the best practices about that. Any other question? Yes?
I have a very naive question. Isn't a lot of this already solved by PKI and MPLS? Why all this instead of plain old MPLS?
PKI and MTLS is something that is not defined to use for storage. And the problem there is how you can verify certificates. We are beginning work to look at that problem. But certificates in storage are different than certificates on web. All the certificates currently defined, what they are doing, they are verifying a DNS name. You need to extend the certificates to verify an NQN, which is not a DNS name. And then there are mechanisms to extensions. And then you have the fundamental problem of what is your certificate authority in the moment in which you are in a separate from the world SAN fabric, and how you are able to verify these certificates. That is not an easy problem, and that is something that we are beginning the work in FMDS, basically in NVMe right now.
But perhaps that might have been the thing to try first, because there's already a lot of infrastructure for
There is a lot of infrastructure which is based on internet access and web access. There is a lot of infrastructure that is all encoded deeply into a web browser or whenever you are using these protocols over there. And porting it on at this level of the stack for storage authentication and storage TLS and so on is not trivial. Again, as I said, we are beginning the work. Yes?
So TCP was not designed for any security. I don't know,
Correct?
my question is it worth using TCP for transporting transport layer memory for storage? Can we do something better than that? Is it time to reduce the
Okay. Let me repeat the question. The question is, TCP has been designed without security. So is it worth to continue to have TCP as a possible storage transport protocol? Well, looking at the customer interest and demand for it, my answer is definitively yes. I guess someone could give you additional information from there. Okay, is definitively yes. And TCP, in terms of security, has been augmented by TLS, transport layer security, that makes TCP totally rock solid. So that's basically what we are talking about here. How to enable to use TLS rather than plain vanilla TCP, so that you get all the security properties that you want. Yes? The two functions are completely independent. AVEs, repeat the question. The question is there any communication between the CDC and the AVE? The two functions are completely independent. CDC is related to discovery. The AVE is related to authentication verification. So from an implementation standpoint, you can collocate the two functions or so on, but that is an implementation choice.
Yeah, the CDC can use the AVE. You can have authenticated connections between hosts of the CDC. And if the CDC wants to use the AVE, they're independent protocols, so they can just all layer and build on top of each other.
The CDC is a controller, and the protocol is defined within a host and a controller, and so yes, the CDC can use the AVE as any other NVMe entity, correct.
Is there any redundancy implemented in AVE? I mean, once the AVE goes away for whatever reason, there's a provisioning for high availability?
Yes. Repeat the question. Is there any redundancy for high availability in the AVE? Because it's quite a critical component in the infrastructure now. Yes. The AVE protocol is designed to be replicated, so you can use different, you can use different IP, you can have multiple replicas of the AVE with the same database available in your fabric, because the only time which you change the AVE database is when you add one new entity to your fabric, only when you provision a new entity. Otherwise, the database of the AVE is always stable, so it's very easy to have, whenever you access the AVE, is a read-only access from a host or a controller when you do authentication verification. So it's very easy to have multiple replicas, and the way which we define the protocol, we have a specific discovery protocol that enables to discover the AVEs with a list of transport addresses, list of IP addresses that enable the host or the controller to connect to multiple replicas of the same AVE. And so if something doesn't work anymore, go to the second one, go to the third one, and so on. Randy, okay. Question, is AVE an open source project or is a Dell product or so on? At the moment it is none of the two. At the moment it's a specification. When the specification is ratified, we see what happens. Randy.
That's actually really close with mine. Okay, I know where to go to get my code. I know where to go to get my subsystem. Who's going to make the AVE?
We encourage you to start the open source project.
Yes.
Do they exchange information with each other? How do they stay in sync? Admittedly, desynchronizing events don't happen very often, but still they must stay in sync. How do they stay in sync?
Okay, repeat the question. The question is, in case of a replicated high available AVE, how do all the replicas stay synchronized and they don't go out of sync in their database? That is part, in a sense, of the management interface to an AVE. Because, again, you change the AVE database only when you provision an additional entity on your fabric and you need to add the secret there. So have a protocol when you do that function that ensures that two-phase commit protocol, whatever, that all replicas are synchronized before you say, okay, now the AVE is updated. Yes?
So, have you thought about additional work on the beyond TLS, like IPsec?
That is, the question is, have you thought to additional work beyond TLS, which is IPsec? Not yet. That would be another possible item. But again, it's completely orthogonal in a sense to the AVE thing, because the DH-HMAC-CHAP is independent from TLS or IPsec or so on. Perform authentication. The AVE is a helper to the authentication function. Yes? Good. I think this is more a comment than a question. Let me repeat it for the audience. It is Google published a protocol which is a simplified version of IPsec called PSP. And so believe that this could be a potential additional security protocol to look at for storage. Any other questions? Or would you like a break? Okay, thank you so much.